So we are in stratified random sampling. In that we have discussed proportional allocation. The next topic to be discussed is optimum allocation. Here we are going to derive the next theorem we are going to discuss is deriving the Neimann optimum formula, and hence finding the variance of sample mean under stratified under optimum allocation. This is also called optimum allocation or Neimann optimum allocation. So first, to derive this, first of all you should find out the Neimann formula for sample size, and then we are going to find out this. Before that, we know that what is variance of y bar st? Variance of y bar st means variance of sample mean under stratified random sample. So its formula is 1 by n square sigma ni into So this is already we have discussed in the previous theorems. Variance of y bar st is this. So to derive the Neimann formula, we are going to make use of Lagrange's function. Lagrange's function. So to frame the Lagrange's function, first of all you should concentrate on two things. What are those two means? The first one, which your Lagrange's function generally used to minimize or maximize. This is a mathematical concept. To frame the Lagrange's function, you should concentrate on two terms which are nothing but the one which you are going to minimize, and what is the condition you are going to make use to minimize the function. So to formulate the Lagrange's function, you should focus on two things: the one which is going to be minimized and the condition which we are going to use. So if you observe these two, we have I think all these are sampling techniques. Under sampling techniques, we always concentrate on the precise estimator, so the precision of the estimator. Precision is nothing but reciprocal of variance. So for any estimate, variance always should be minimized. So the one which we are going to minimize is nothing but variance, and the condition which we are going to use here is nothing but total sample size. Total means sigma. Total sample size from each stratum is small n. So if we denote the Lagrange's function with phi or any other symbol, Greek symbol like phi, first you should write the one which we are going to minimize. We are going to minimize the variance. Variance we indicate with variance of y bar st. So this is equal to variance of y bar. You are going to minimize this plus lambda. Lambda is called Lagrange's constant. Lambda into the condition which we are going to use. The condition which we are going to use is nothing but sigma ni minus n. If you bring this to the LHS, condition becomes sigma ni minus n. So to frame the Lagrange's function, you should identify which you are going to minimize and what is the condition you are going to use. So here we are going to be always going to minimize the variance, and the condition here is nothing but ni is equal to ni. This is the way of formulating phi. Phi is equal to variance of y bar st plus this is called Lagrange's multiplier or constant lambda into sigma ni minus n. Our aim is nothing but to formulate the Neimann formula. For that, you should find out the value of n. Expression for ni you should find out. For that, you are going to minimize the Lagrange's function. You know that either minimization or maximization involves finding the partial derivatives and equating it to 0 and finding the second derivative. You know this well. So you need to find out dou phi by dou ni, which is equal to, what is the formula for variance of y bar st? Please rewrite this. So we are going to find out the derivative with respect to n. So dou by dou ni of, if you observe here, this is a constant. Okay, this is a constant, this is a constant. So if you take out this, this can be taken out of the derivative 1 by n square sigma ni into, let us take this ni to each of these terms. So ni by ni minus ni by ni is 1 into so here 1 by n square. If you observe here, you are going to differentiate with respect to n. So dou by dou ni of the first term, which is nothing but, if you multiply with this, you will get sigma ni square by ni minus, I think if you into si square, let us multiply this also, ni into ni square by ni into si square. Next term ni into 1, ni into si square plus dou by dou ni of lambda can be taken out as it is independent of I, ni minus n. So if you find out the derivative partially with respect to ni, you won't get sigma here. So here you will get ni square into si square, but it is in the form of 1 by x. What is the derivative of 1 by x? Its derivative is minus 1 by x square. So you will get minus 1 by ni square. So here you don't have ni here, partially it can be treated as constant 0 plus lambda into, what is the derivative of ni? You won't get sigma while differentiating. So here sigma is skipped. Dou by dou ni of means you will get 1. There is no ni here, 0. So you got the term 1 by n square ni square si square by ni square plus lambda is equal to 0. So here we are going to find out the expression for ni. So here what is the last expression you got? As dou phi by dou ni is equal to 0, you will get minus 1 by n square, you won't get sigma, ni square by ni square into si square plus lambda is equal to 0. So as I said you that you are going to find out the expression for ni. So let us take all the terms to the RHS except ni. So you will get minus ni square by si square by n square by ni square is equal to minus lambda. Minus will cancels and you will get ni square si square by n square ni square is equal to n. As you have from this, what will be ni square? If you cross multiply here, to lambda is equal to ni square on cross multiplication. You want to find out the expression for ni. So ni square will be ni square by ni si square by n square lambda. So ni will be root over ni square si square by n square lambda. So you will get ni is equal to ni si by n into root lambda. So you have obtained the formula for ni. What it involves? Capital Ni, capital Si, capital N, lambda. So all are known to you except lambda. If you want to find out the value for Ni, all these are known to you except lambda. So this is a partial, you didn't get the correct expression or the required expression for Ni because it is involving lambda. So let us give equation number 2 to this and let us try to evaluate lambda, and again let us substitute lambda here so that you will get complete expression for Ni. Okay, that is called Neimanns formula. This is what we are deriving. So to find out this, let us sum equation number 2 over I. Means let both sides you take summation with respect to I on both sides. So what is sigma Ni? What is the condition you are making use of? Sigma Ni is equal to n. So in place of sigma small ni, you can substitute n. N is equal to sigma ni si by n root lambda. So you are going to find out lambda here. So what will be n? N root lambda is equal to sigma ni si. From this, root lambda will be sigma NiSi by Nn. So let us take this as equation number 3. Let us substitute this 3 in 2 to get the Neimanns formula. 3 in 2. What is 2 actually? 2 is nothing but expression for small ni, which is nothing but NiSi by n into root over lambda. As I said you that all these are known to you, only this is unknown. For that you have to summed equation number 2 over I. From there you got the expression for lambda, which is nothing but this. Let us substitute this in NiSi by n into sigma NiSi by Nn. So these two cancel. So you got Ni is equal to NiSi by sigma NiSi. Means the same term with sigma and without sigma. If you observe Ni, you have all the known quantities NiSi, no lambda here. So this is called Neimanns formula. So if in the exam you got only Neimanns formula, means you can stop there. Otherwise, if you have another question called variance of y bar st under optimum allocation, you are going to extend the theorem. Okay, thank you.